All right, so to begin with, let's talk about Dalton's law and when we talk about gas exchange. All right, so with Dalton's law, this is going to be the total pressure of gas in a mixture that is equal to the sum of the pressures that each gas in the mixture would exert independently. Okay, so when we talk about the different gases, we're talking about water vapor, carbon dioxide, oxygen, and nitrogen. Oxygen is going to make up 21% of the atmosphere, and then we'll have with nitrogen, this is going to make up 78% of the atmosphere, and then what we'll have is 21% being of carbon dioxide. Okay, and so the partial pressure then is going to be the pressure that a particular gas exerts independently. So the sum of the partial pressures of nitrogen, oxygen, carbon dioxide, and of water is going to equal 760 millimeters of mercury. All right, and so since oxygen is 21% of the atmosphere, then what we'll have is the 760 millimeters of mercury times that by the 21%, and so we'll get about 159 millimeters of mercury. Okay, so for instance, then partial pressure of carbon dioxide, same equation, 1% then is going to be about 40 millimeters of mercury. Now, when we are comparing the atmosphere within, or the gas within the atmosphere to the gas within the lungs, we are comparing the partial pressures then of the gases that we find there. Okay, so what I want to draw our attention first to is down here where the total pressure within the atmosphere of inspired air is going to equal 760 millimeters of mercury, and that will equal the alveoli air within our lungs to be also at 760 millimeters of mercury. The difference that we'll see is due to the gases themselves are going to reflect differences in pressure changes. Okay, so within the alveoli, what we have is that the percentage of oxygen actually decreases. So here we have oxygen at 105 millimeters of mercury in the lungs compared to that within the inspired air of the atmosphere. And then carbon dioxide is going to be higher as compared to that of the atmosphere. So these changes in partial pressure is going to be responsible for then respiration, for inhalation and exhalation. But both of which are going to have, though, the pressure being equal at that 760 millimeters of mercury. All right, for our partial pressures, what we have is a state of equilibrium where we're going to hit a maximum value. And so this is Henry's law. And so our maximum value then is going to be 760 millimeters of mercury. Now, we can have three different variables, though, that will affect this state of homeostasis, of equilibrium. Okay, so the first thing is going to be the solubility of the gas in the fluid. And so this, though, is held constant. The second thing, though, that can affect it for the body is going to be temperature of the fluid, where we'll have more gas dissolving in colder liquid, but that doesn't change for the blood, because within our blood system we have a very fine and small range for temperature of our blood. Okay, so the main variable that is going to affect the gas is going to be the partial pressure. Okay, and so this is going to be highly dependent on partial pressure of carbon dioxide and of oxygen in terms of diffusion then for these two gases within our bloodstream. So when we look at the measurements of partial pressure of both oxygen and carbon dioxide, let's look at the two different systems of the pulmonary circuit and the systemic circuit. Okay, so what we have here in this diagram is here, this first one is going to be the partial pressure of oxygen is going to be about 40 millimeters of mercury when it comes from the pulmonary arteries, and then partial pressure of carbon dioxide is at 46 millimeters of mercury. So then within the capillaries of the alveoli, then we are becoming oxygenated, so we are gaining an increase in partial pressure of oxygen, but then we are decreasing the partial pressure of carbon dioxide because oxygen is coming into the lungs and we are exhaling carbon dioxide. So then we lose a little bit of the oxygen due to diffusion, and some of it just remains within the lungs themselves. And so this number just drops slightly to 100 millimeters of mercury. And then this is going to travel through the heart and then into the systemic circuit, where now the arteries are bringing this amount of oxygen into the capillaries within the system. And so now we're going to be losing oxygen, and then we are gaining carbon dioxide. So within the systemic veins, then this is why we see an increase now in carbon dioxide up to 46 millimeters of mercury compared to this 40 millimeters of mercury. And now our oxygen levels have dropped, where now it drops to 40 millimeters of mercury, and then from 100 millimeters of mercury. And so this is going to be significant because this is the driving force of inhalation and exhalation, and keeping our oxygen and carbon dioxide levels differences throughout the body. So with our pulmonary circulation, this is the rate of blood flow going through the pulmonary circuit. And so this has to equal the flow rate going through the systemic circuit. All right, so if we remember, our cardiac output is about 5.5 liters per minute. And so the driving force, though, in terms of pressure, is only about 10 millimeters of mercury. So the pressure difference between the left atrium and the pulmonary artery then is this 10 millimeters of mercury. So when we have then blood flowing to the alveoli, is going to be increased when they are full of oxygen, and it will be decreased when they are not full of oxygen. And so this is the opposite of the systemic arterioles that constrict when partial pressure of oxygen in tissues is high. And so this is important because this ensures that not only tissues that need oxygen are sending blood. Okay, and so this is another role for autoregulation, where the pulmonary arterioles then are going to constrict when the alveoli partial pressure of oxygen decreases. And so that we have equal blood flow that's going to circulate for both the systemic and pulmonary circuit. So this is achieved then by having pulmonary vascular resistance that is going to be low, and this helps to prevent edema within the lungs so that we don't have overflow of fluid going to them. Right, the cool thing about pulmonary circulation is that for a fetus, they have a very high vascular resistance, and this is because the lungs are partially collapsed. And then right after birth, then this resistance starts to decrease, and so the vessels are going to start opening due to the pressure changes now to their atmospheric environment. And then for the interpulmonary pressure is also changing due to now the pressure changes within the atmosphere. And so this is also causing physical stretching of the lungs as they're starting to take in their first breath, and then the dilation of the pulmonary arteries are going to increase because now we're increasing the amount of alveolar partial pressure of oxygen.